So we're going to learn about a new type of geometric object in this section, and it's called a secant. Now let's quickly define what a secant is. A secant is any line or a line that intersects a circle at 2 points. So a tangent, remember, a tangent intersects a circle at exactly 1 point. So a secant is a line that intersects a circle at 2 points. So if we look at our diagram down here, we see a couple secants. We see line DB that is intersecting the circle at points D and B. We see line AC that's intersecting the circle at points A and C. So we have a couple secants. Now, when I have these two secants drawn here, you'll notice that they are intersecting at point E. Right? Point E here is our point of intersection between these two secants. And when those two secants intersected, they formed 4 angles, right? Now, I'm looking at angle 1 here, and I know that this angle over here would be the same as angle 1 because they're vertical angles. And let's look real quick and see if there's anything that we might be able to say about the measure of angle 1 and how it relates to any of these arcs that we see that are being intercepted by these intersecting secants, right? These two secants intersecting, they're kind of chopping our circle into 4 different arcs. We got arc BC, arc CD, arc DA, and arc AB. Right? We have these 4 different arcs that have been created when I had my 2 intersecting secants. And so the first thing I want to look at is there any relationship between those arc measures and angle 1? And I'm going to do a quick proof to you to show that there is actually a relationship. And the first step in this proof is actually to draw a new segment right here, right? So we drew segment AB, and now that one of the things that did is it formed this triangle AEB, okay? Now, if I look here, it also formed an inscribed angle. Actually, it formed 2 inscribed angles. It formed one angle called angle BAC. That's an inscribed angle. And its measure would be half of the measure of arc BC, right? It would be half of the measure of arc BC. So this angle kind of goes with this arc. But it also formed an angle right here called angle ABD, which is an inscribed angle. And it's intercepting arc AD. So we know that that angle would be half of arc AD's measure. So from that, we can actually, I'm going to show you how we can actually say something about angle 1. Now, if I look at angle 1, it is an exterior angle to this triangle. So like we've talked about before, that means that the measure of angle 1 would be equal to the measure of angle BAC plus the measure of angle ABD. And that's just the idea that this exterior angles measure will be the sum of the 2 remote interior angles. Now you'll notice those 2 angles are the ones that I've kind of highlighted here. They're these inscribed angles, right? Angle ABD is this angle, and angle BAC is the one that I've kind of highlighted in that color. And so what I'm going to do now is I'm going to take this equation and I'm going to substitute for the measure of angle BAC. I'm going to say, well, that's half of the measure of arc BC. And for the measure of angle ABD, I'm going to substitute half of the measure of arc AD. So now angle 1 is equal to half of BC, arc BC, plus half the measure of arc AD. And then from this, since I notice that there's 2 things here that are being multiplied by 1/2 and added together, I'm actually going to factor out that 1/2, and that's going to leave me the measure of arc BC plus the measure of arc AD. Just a little basic algebra here where I factored out this 1/2 from this side of that statement, so it now says 1/2 the quantity measure of arc BC plus measure of arc AD. And that's kind of the conclusion that I wanted to be able to draw. That yes, there is a relationship between angle 1 and some of these arcs that I created with these 2 intersecting secants. Angle 1's measure would be whatever I get if I added BC to get arc BC's measure and arc AD's measure. If I added those together and then took half of that total, that's going to be the measure of angle 1. So that's actually going to lead us to our next theorem that we're going to learn. It says the measure of an angle formed by two secant lines that intersect inside a circle. So our two secants have to have their intersection point inside the circle here, is equal to half the sum of the arc intercepted by the angle. So half the sum. So sum indicates that we're going to add two things together. One of the things we're going to add is the arc that's intercepted by the angle. The other thing is we're going to say, and the arc intercepted by its vertical angle. Right? So we have these two intersecting secants. They create four different angles, but we know that they kind of come in pairs of vertical angles. So if I wanted to know the measure of angle 1 here, I can say the measure of angle, I'll write it up here. The measure of angle 1 is going to be half of the sum of its intercepted arc, so that's x, and the intercepted arc of its vertical angle down here, which is this y here. So angle 1 would be half of whatever this arc is plus whatever this arc is. And that's going to be theorem 10-10. Now there's going to be a second theorem here. Let's see what our next theorem is going to tell us. The measure of an angle formed by two lines that intersect outside the circle. So now we have two lines intersecting outside the circle. Whereas before our intersection point was inside, now it's going to be outside here. And actually what's going to happen here, I'm not going to go through the proof necessarily for it, but if you look at this angle 1, it's actually intersecting two arcs. It's intersecting one here closer to the vertex, as well as intersecting one here that's kind of like on the opposite side of the circle from it, farther away from the vertex. And if I want to know the measure of angle 1, what I can do is I can take the measure of angle 1 would be equal to half of now the difference between those two arc measures. So if I take the big one minus the little one and then take half of that, that's going to be the measure of angle 1. So in words here, I'll say the measure of an angle formed by two lines that intersect outside a circle is half the difference of the two intersected arcs. So remember, difference is indicating that we're subtracting. So this is saying, basically it says, subtract the two intersected arcs, take the bigger one minus the smaller one, and then cut that number in half, and that will be the measure of your angle. Now there's kind of three ways that can happen, right? Case 1 is maybe the most simple to visualize. We have our two lines that are both going to be secant lines. They're going to intersect the circle twice each. All right, and then here we have their intersection point, and so we have that angle that's outside my circle. But the other possibility, because it just says the measure of an angle formed by two lines, well, maybe one of them is a secant line, and the other one is a tangent line, okay? So that in that case, we would still have two intercepted arcs, right? We'd have this arc here that's close to my vertex point, and then we'd have this arc out here that's a little farther away from my intersection point. But I'm still going to say that the measure of angle 2 is going to be half of the difference between those arc measures, so D minus C. Case 3 would be where I actually have two tangent lines intersecting the circle, right? And their intersection point is here outside the circle. Again, they're going to be intercepting two different arcs, one that's closer to the vertex, and then one that's like farther away from the vertex here. And I'm still going to say that that angle's measure is half of the difference between those arc measures. F minus E, cut that in half, that's your angle measure there. Okay, so now we're actually also going to look at what happens when we have lines intersecting or segments intersecting, but we're interested in the lengths of those segments, okay? So we have a theorem called Theorem 10-12 that says, for a given point and a circle, the product of the two segments from the point to the circle is, so this is kind of a weird way of wording it. Basically what we could be looking at is one of three different cases. So let's say we have this point here that is somewhere inside the circle. It would even technically work if the point was the actual center of the circle, right? So we have that point here. And then if we draw two chords that go through that point, right? And a chord we know has endpoints that are going to be on the circle. So we draw a chord here. I'll kind of color it in this green color, right? So we have this chord here. And then we draw another chord. I'll make it this orange color here. And they're kind of two chords that both intersect at that point, that random point that we've kind of chosen right here. Well, then you can see we actually kind of have four different segments that are going from that point out to the circle. We have this segment here, which has a length of A, and then going in the exact opposite direction, we have this segment, which has a length of B. We have this segment here, which has a length of D, and in the exact opposite direction, we have this segment here, which has a length of C, right? Now, there is a relationship between the lengths of those segments, the lengths of segments A, B, C, and D. And that relationship looks like this. The products of the two segments from the point to the circle, that product, remember, so that means multiplying, right? So if we multiply these two things or these two things, that product will always be constant. Or we can say equal. So what does that mean? Okay, that's kind of a weirdly worded theorem. So I always just try and think, well, what does that mean in one of these cases? Well, here's that case again where my point is inside the circle and we've drawn a couple chords here, and those chords have been kind of divided into two parts apiece by that point. If I take A times B, right, let's actually color code these a little bit differently. Let's put slightly different colors on these. So we'll make B this color here, and then we'll make D this brighter red color. Let's try it out again for B. Okay. Then what that means is if I take A times B, that will always equal C times D. And it doesn't matter where I move that point and what those chords look like. If I pick any point inside the circle and I draw a couple chords that go through that point and intersect at that point, and those chords get divided into their two parts by each other. If I multiply those two parts and I multiply those two parts, that product will always be equal. And it also works if your point is outside the circle. So if my point is outside the circle, and now I draw what I might call a secant segment, right? I draw a secant segment. In this case, if I take the part that's outside the circle, n, times the entire secant segment length, which will be n plus m, that product of outside times the entire secant segment will be equal to outside part here, q, times entire segment there, q plus p. Or if maybe I have a point outside the circle, and one of my segments is a tangent segment and the other one is a secant segment that's going to hit the circle twice. In that case, if I take x and I multiply it times itself, so basically if I do x squared or x times x, that product would be equal to this first segment, which is from that point to the nearest point on the circle, times the length of the segment that goes from that point to the farther point on the circle, which would be z plus y. Those relationships will always be true. And so the way this is worded, what that's saying is, if I take a point here, and I go to my circle in this direction, and I go to my circle in the exact opposite direction, and I multiply those two distances, and then I go from that same point to my circle this way, and to my circle in the exact opposite direction, and I multiply those two distances, those products will be equal. Or if I put my point outside the circle, and from that point I go to the closest point of the circle along this line, and I go to the point that's like on the opposite side of the circle over here, and I multiply those two distances. So n times this entire thing, which is n plus m. That product equals q times q plus p. Or if one of them is a tangent, and I do that twice, so x times x would be equal to z times z plus y. All right, and that's a lot to remember, but it's kind of an interesting relationship, and so we wanted to mention it and kind of take a look at that.